First day was first law, and you know all the demos that went with it. Hopefully you put those in your notes someplace so you can refer to them later. So when I say, what law does the quarter, card, and jar demo illustrate, you're going to say the first law. And why is it that the quarter falls into the jar? You're going to say the quarter has inertia. All of those things illustrated the law of inertia. The second law included the hammer drop, the book and paper drop, the ball drop versus the ball toss. That was that little demo thing that shot the ball out and dropped it. And the washer drop I did over there. All of those had to do with force, gravity, air resistance, and terminal velocity. If all you know is the definition for each of those, you really don't understand the concept. I want you to be able to explain to me why the piece of paper in a ball falls faster than the same weight piece of paper that's flat. I want you to understand what gravity is doing to objects. That gravity causes all objects to accelerate at what rate? 8 meters per second squared. Every second they're going to go 9.8 meters per second faster until they reach their top speed falling, which is the terminal velocity. What three things affect the object's terminal velocity?
Size, speed,
and speed that it's moving. The faster it's moving, the harder it is to go faster. And the shape and the size will affect the amount of air resistance. So that was all yesterday. This last one is a famous law I'm sure you've all heard of. It's often known as the action-reaction law. And it goes something like this. For every action there is
equal and opposite.
There you go. And those are two important things, equal and opposite reaction. To just say for every action there's a reaction is not sufficient. What Newton said is for everything you do, there's going to be something that's equal and opposite in reaction. And he goes on to talk about this thing called momentum. Okay? Remember, we talked about inertia. And inertia sounds a lot like momentum. An object that's just sitting there, like my water bottle, has inertia. It's going to resist any change in its motion. I'm going to have to push it and apply a force to get it going. Likewise, it's going to continue to go unless some force acts on it. But I wouldn't say the bottle sitting there has momentum. If it is just sitting there. It doesn't have momentum unless it is moving. Momentum involves movement and involves mass. The more mass I've got and the more speed it's got, the more momentum I've got. And that's the formula for it that you're going to learn more about in your reading today. These are the demos that go with the third law. And again, I'm going to expect you to know, be able to make predictions on these and explain your prediction. Why do you think it will turn out that way? So let's do those now. Let's see if you can predict. First of all, over here, this little guy is called a Newton's Cradle, after Isaac Newton. Each of the 5 balls have identical mass. If I pull back and release one ball, what do you predict will happen? One will come out the other side. Okay, if I pull back and release 2, what will happen?
2.
If I pull back and release 3, what will happen?
Go back.
Okay, we've seen lots of different answers there. 4. Pull back and release 5.
Go crazy.
If I pull back 1 on each side, an equal distance, and release them. Okay? What if I pull back 2 on one side and 1 on the other side? If you understand Newton's law, third law of motion, for every action there's an equal and opposite reaction, you can, without any hesitation, tell me what's going to happen there. Now, this is a lot simpler, believe it or not, than this demo. That one involves 5 balls, but this only involves 2. The difference is those have identical mass. Every ball has the same mass as the next one. What's going to happen when the mass is different? Some of you anticipated that the mass of one ball would strike it, causing the mass of this ball to come out the other side. But if this ball has much more mass than this one, what do you predict will happen when I drop them so that one ball stays on top of the other one and they hit the ground? What do you think is going to happen? I'm going to drop them from this cylinder up at the ceiling, and we're going to see what's going to happen when they hit the ground. So it's just like this guy. One ball hits the other ball. But now the balls don't have all the same mass. This one has a lot more mass. The golf ball has a lot more mass than the ping pong ball. So predict in your mind what you think will happen with that one. The pendulum. Pendulum, I know you can predict this one because you already told me the law. For every action there is. You truly believe that? Do you really? Are you willing to put your dental work on the line?
No.
If you truly believe and you truly trust science, you would do this demo. You would come up here, you would have this 1 kilogram weight hanging from this string. You've got a pendulum, you're going to hold it right next to your teeth, and you're going to release. And you know that for every action there is, therefore the weight should not come back any further than it went out, right? In fact, will it even come back as far?
No.
What things would resist it from coming back all the way? Why would it not be equal and opposite? Air resistance and gravity. If I didn't have air resistance and I didn't have gravity, that pendulum would keep doing that forever, ever, and ever. Okay? That momentum would be conserved. That's why we call this the conservation of momentum. Is sometimes what this law is called, or the action-reaction law. The last one is the one I left you with yesterday to ponder and to get into a debate with your parents. Did anyone talk about it with their parents? And what did you conclude?
That it wouldn't move.
Okay, any other ideas? How many think it'll go to the right? How many think it'll go to the left? Then what else? What other answers are there? How many think it won't move then? Okay, and the rest of you aren't even guessing, big chickens. Like I said, this is one of the demos that I discussed with my father. We got in a big debate about it. He just didn't believe me. You know, sometimes things in physics don't go along with what you would expect. They may be the exact opposite of what you would anticipate. But if you understand this concept of action-reaction, you should be able to predict that accurately. If you understand momentum, you can easily predict what's going to happen here. What two things determine an object's momentum?
Mass and velocity.
Mass and velocity, or you could say mass and speed. So, the greater the speed, the truck is going down speedway, the more momentum it has, the harder it's going to be to stop it. Remember, objects that are just sitting there don't have momentum. They do have what? Yeah, and therefore inertia. So first law applies to it. They do have inertia. But when an object is in motion, boom. If it has mass and it has speed, it has momentum. If this ball was bigger, I'd have even more momentum. All these 5 balls in this Newton's cradle, that's what this is called, have the same mass. Therefore, if I pull back one ball and release it, what's going to happen? One will go out the other side. According to Newton's law, we say this is conservation of momentum. The energy that went in is what I got out, with the exception of some outside forces. When one ball strikes the other one, some of that energy is used to make sound. Some is used to make heat. And some of that motion is slowed down by gravity and air resistance. Those are the outside forces. If it wasn't for those outside forces, though, this was the big idea that Newton said. This would keep going on and on forever. The momentum is not lost, it's transferred. We say it is conserved. And when you conserve water, you don't waste it. Conservation of momentum means that momentum doesn't disappear. It stays in this, we call this the system. It stays within the system. Now, there are forces. There is air resistance. There are other ways that that energy is transferred. But otherwise, it's going to be used for motion. Now, if I pull back 2 balls and release, what's going to happen? 2 are going to come out the other side. If I pull back 3 balls, what's going to happen? Nothing. I have to release it first. 3 in, 3 out. 3 in, 3 out. One of them travels with the group. Okay? If I pull back 4, what's going to happen?
3 are going to go on the other side.
Suckers. Nothing. I have to release it first. Right? Gotcha. Second time. Pull back 4, 4 in, 4 out. I have 3 travelers. 3 that go back and forth. If I pull back 1 on each side, what's going to happen? Nothing. I have to release them first. Right? The energy is transferred back out. It's like a ball bouncing off the wall. And of course, you know, the farther I take this back, the farther it's going to come out on the other side. If it wasn't for gravity and air resistance and changes in energy, this would just keep going on and on forever. The momentum is conserved. Okay? So, what Newton did is he took it a step further. He actually quantified this. He said that mass and speed determine the momentum. Here it's simple because all the balls have the same mass. I pull back a little way, I get a little bit of speed, I get a little speed on this side. I pull back a lot farther, I get more speed, I get more speed on this side. No big shocker there. But what's really interesting is when you look at objects that have different masses, like this ping pong ball and the golf ball. What do you predict is going to happen when I drop this from the ceiling, Anthony?
The golf ball's gonna hit the ground and that comes off the ping pong.
Okay, what do you think, Nathan?
The golf ball's gonna bounce a little bit.
Okay, if you've ever watched a football game where, let's say, the running back, my ping pong ball, was trying to carry the ball around the end, and the big old linebacker sees him, and he comes along, and the linebacker weighs a lot more than the little running back, and he hits him, and it doesn't look like he's going that fast, and he hits him, but he has a lot more mass and momentum, you're right, then what happens to that running back? He goes flying. You're like, whoa, what a hit, right? Well, if I drop 2 identical spheres from the same height at the same time, which one will hit first? Same time. But what if one's heavier than the other?
Doesn't matter.
Doesn't matter. Same time. It's size and shape that affect the rate of fall. Gravity's the same for the heavy and the light one. So, if I drop these 2 from the same height, they hit at the same time, but one of them has a lot more mass, right? And if it has more mass, but it's going at the same speed, it must have more momentum. Here, the momentum from the one swinging ball was transferred to the other one. And because the balls had the same mass, what you put in is what you got out. Here, the balls don't have the same mass. I've got one with far less mass. You just hand it to him at very green. I got one with far less mass. So according to Newton's law of conservation of momentum, it says that the P has to stay the same. The momentum going in has to be the same as the momentum coming out. This has to be the same. Well, the ping pong ball is going to be in the way of the golf ball when it bounces off the ground. So that energy that the golf ball had is going to be transferred to the ping pong ball. Either that ping pong ball, in order to keep this number the same, either that ping pong ball has to gain a whole lot of mass, or it has to gain a whole lot of velocity. Okay? Well, it can't suddenly become heavier, but it can suddenly start moving faster. And that's what you're going to see here. You could do the same demo as you see up there. I've illustrated a basketball and a tennis ball. You can do the same demo with those 2, as long as there's a big difference in mass. 1, 2, 3.
Oh my goodness.
Okay? The ping pong ball gets a lot of extra energy. The energy came from the higher mass. Okay? The energy came from the higher mass. It had to go somewhere. All that energy from the bounce was transferred into this ball. Just like a big heavy guy hitting a little light guy, the light guy goes flying. Make sense? The momentum is conserved. It's still there. I'm going to ask you to solve math problems using this formula. It's no different than when we did our force equals mass times acceleration. If I give you a problem like this, consider this one. I've got an elephant walking slowly, and I've got a bullet fired from a gun. Which has more momentum?
It depends
Good answer. It depends on what, Zach?
on the velocity and the mass of each.
Exactly. Like, let's just say, for instance, that the elephant is 6,000 kilograms. That's way high, but just play along. And it's walking at 1 meter a second. The bullet, let's say, is 1 kilogram. Way too high, but. And it's moving at 6,000 meters per second, which has more momentum.
Same.
They're the same, okay? You may say, well, no way, that elephant's so big, he's got to have more momentum. Yeah, but he's moving slowly. This thing's very light, but it's moving fast. So you can't tell me how much momentum an object has unless you know both things, mass and velocity. When I ask you to solve for momentum on the homework, you're going to be using mass in kilograms and velocity in meters per second. That means that's the label you're going to put on your answer. Don't confuse that with the label you got from force. Remember that? That was kilograms times meters per second squared. And that we abbreviated with N. Okay, this is not newtons. So there should be no N, there should be no squared. If you're solving for momentum and you're trying to put the label on your answer, see, some of you are writing this down, smart people, and you're solving for momentum, this is the label that goes on your answer. AG dot M/x. That's the label on the answer, not newtons. Newtons comes from mass and acceleration. This is different. Okay? Any questions on that? Some of you didn't write it down, so I hope you remember when you get your homework. All right. We're going to do the pendulum one here in just a second, but before that I want to ask you about the raft. How many say the raft will go to the right? How many say it'll go to the left? How many say it'll stay put? Okay? My dad insisted that the raft would go to the right. And his logic, and I understand it, and what some of your parents might argue, is that whenever the sails, let's say these are sails, whenever the sails are full of air, the boat moves. And that force is going this direction, therefore the boat goes that direction. What he failed to see is that there's two things happening here. There's two forces. There's an action and a reaction force. Okay? Now, if you break it down like this, you can understand why the boat goes nowhere. That is the correct answer. If I took a big giant fan like this, and let's say it was on wheels, and I had it blowing air at a wall, say it was a giant movie fan, what would the fan do? It would go backwards. It would apply a force this way to the wall, and then it would roll backwards. But this isn't on wheels. It is attached to the raft. Therefore, the fan is applying a force this way, and it's trying to push itself that way at the same time. Okay? Does that make sense? It's like if I do this, and I don't have good friction with the ground, my feet will push back. Okay? It's applying a force the opposite direction. Action, reaction. But look at what this force is doing. Because all of that energy from the air is being captured by the fan, it's pushing, by the sail, it's pushing the boat that way. So you've got the sail pushing the boat that way, and you've got the fan trying to go the opposite direction. For every action, there's an equal and opposite reaction. What I try to explain to him is it doesn't matter that the sails are full of air. What matters is where the force is coming from. Okay? If you were out at sea and there was no wind whatsoever in your sailboat, do you think you could get the boat to move by going over to the sails and pushing on them? No. You're applying a force to the sails, and you're applying a force to the boat. but you're also standing on the boat. And you're pushing with your feet the opposite way. If you want to push this boat away from the dock, you can stand over here, you know, have a stick in your hand, and you can push yourself away from the dock. Because you have something off of the boat that you're pushing off of. Likewise, if you've seen those boats in Florida that have a fan, do they blow into a sail? No, they blow out this way. Well, what is that pushing off of?
The air.
The what?
The air.
Air. The air, all the air here. That force is pushing off of the air, and it's pushing the boat the opposite direction. Of course, if that wasn't attached to the boat, the fan would just fly right off the other side of the boat. Okay? It's pushing off of the air. In order for this boat to move forward, it has to push off of something outside of the boat. It could be the air, or it could be the wind comes in and hits the sail. Something off of the boat is hitting the boat. Okay? When you sit in a rowboat and you make it go forward, you're applying the oars to something off of the boat, which is the water. You have to have something to push against in order to get it to go. Okay? How many think they understand this one now? Great. It's a fun one to argue because people will insist that it will go that way. And it's not true, because the forces are canceled out, equal and opposite. All right, who truly trusts science? Okay, Zach, come on up. You'll show me that you truly trust science because without hesitation, you will not flinch. You know that for every action, there's equal and opposite reaction, so you'll hold this right to your chin, thusly, and without moving or flinching, you'll release, and you'll let it come all the way back without fear that it's going to hit you in the teeth.
Do I get to catch it?
No, you don't get to catch it. You got to just stand there and stare at it. Everyone watch him carefully. See if he truly trusts science. Don't flinch. Oh, you moved. You moved. No, it wasn't. You didn't trust science. Someone else want to try? Come on, Matt. If you truly trust science, you won't flinch. I will tell you, since Zach is done and he knows, it looks like it's going to hit you. It looks, from that point of view, it looks like it's coming a lot closer than it actually does. Just don't lean forward. Stay put when you release. Oh, you move forward. It's going to hit you. It's going to hit you. Ah, he did trust science. Very good. All right. Before I give you your homework, I want to tell you a little story. My story is titled, What Goes Around Comes Around. Or, subtitled, For Every Action, There's an Equal and Opposite Reaction. Okay? So, by the way, the assignment you did yesterday, you didn't have enough time. A lot of you didn't have enough time. I'm going to lower the required points on that, so don't worry about that. I didn't give you enough time for that. So my story goes back to when I was in elementary school. I went to Van Horn. Did you guys go to Van Horn? Okay? Yeah. And like a lot of you, at some point in our lives, we encounter bullies. My bully's name was Raymond. He lived right down the street from me. Okay? He made my life miserable. Don't laugh at my pain. So Raymond made my life miserable. He would just pick on me, beat me up every day after school. I would try to find another way to get home. I'd run down the alley. I'd leave a different route. I'd try to get out early, whatever I could to avoid this kid. And I remember on this one particular day, it was lunchtime, and nobody was really paying attention to what the kids were doing. There were monitors, but they were like way over there. And I was over in the corner, over by where the desert is, close to Udall Park now. And there's sometimes debris would wind up on the field there, and I was looking for something, to get myself into trouble. I was just goofing around by myself, and I found this big old long piece of wood. Oh, this is cool. What can I do with this? Okay. So I'm looking at this big piece of wood, and then I notice over here this big rock. I got an idea. I've been watching the circus, so I take the big rock and I drag it over here into some open space. Some of you see where this is going. And I took the big stick and I laid it across the rock, and I stepping on one end, it's like a teeter-totter. Okay. Oh, a catapult. Yeah, I could get things way up in the air. So the board was about that long, okay? It wasn't as long as I was tall. And I didn't understand physics. I didn't understand trajectories, okay? But I thought I was going to make this cool catapult to shoot this thing up in the air. So I get myself a pretty good sized rock and I put it on, don't be laughing at my misery. I get this rock and I put it on one end of my little catapult there. And I stand back and I evaluate the situation. Okay, I shoot that rock right in the air. All right, here we go. Ready, set, get myself a running start, jump up. Boom! Boom! Okay? Because of the way I had that thing set up, that board was shorter than I was tall. The rock was thrown straight into my head. Now, if you ever get hit in the head with a rock and you start bleeding, you know you bleed pretty badly. I was just gushing blood and I had it all in my hands. I'm like, well, the teacher's going to notice this. And I'm starting to cry and realize this is going to be quite embarrassing. What am I going to say? And I'm starting to get the attention of the monitors. The monitor comes over and says, what happened? Well, the only thing that occurred to me was Raymond did it. Raymond threw a rock at me. Now, Raymond already had a reputation. He picked on other kids too. So there was no question. Well, if he said Raymond did it, Raymond did it. And I still remember this like it was yesterday because I was sitting in the nurse's office, and this was back in the day where they still did corporal punishment. You got a spanking. And I was sitting in the nurse's office getting my little butterfly bandage on my forehead for my cut, and I could hear, whack, ah, whack, I didn't do it! You know, Raymond crying away in the other room. And that day I learned Newton's third law. For every action, there's an equal and opposite reaction. Or what goes around comes around. What occurred to me was